Okay, welcome to the last lecture of the semester of our course on elliptic curves. So I still have one piece of paper from the last lecture that I want to talk about. In the last lecture, one result that we had was that if an elliptic curve has complex multiplication by something with class number 1, then the J invariant, I write it like this, is an integer. So Z0 was the CM point that comes from the kind of analytic side, and J is the modular J function. Which looks like, well, it's a series that starts at -1. Yeah, I will go into detail in a minute. So one interesting example that you will see in the literature quite often, I think, is the following. With a nice consequence. So we take the following CM point, which belongs to an elliptic curve that has complex multiplication by the ring of integers of q square root of minus 163. And this field has class number 1. So that means J of Z0 is an integer. Okay, what can we do with that? Now, if we look as a black box, because we didn't really treat it here, if we look at the this J function, this looks like this. Where Q is the log again probably is this. So it's a series in e to the 2 pi I Z0. It starts at -1, then it has a constant term, and then it has more terms. And well, the interesting thing is also all the coefficients that come here are also integers, and this is also an integer. So what does this tell us? So it tells us that this whole thing is an integer. Now, what happens if we plug that in here? So it means that e to the 2 pi I I didn't say what Z0 is. So Z0 is the generator of this ring, and this is this. So Okay, so if we now have this, if we now plug in for z0, this 1 plus square root of minus 163 over 2, yeah, it's a bit complicated with this minus and the over 2, but if you plug it in and compute what it is, then you see that this is the same as this. Then we have another integer, and this gets very small very fast. So this is something like, I think, 0. Then maybe 5 zeros, and then we have something. Okay, why is this interesting? Well, it's interesting because, well, we have something very small. We can basically forget about this. We have an integer, and all this together is also an integer, which means that e to the pi times square root of 163 is almost an integer, which is very nice and surprising, I think. Yeah. So that was the example that I wanted to give to the whole complex multiplication topic from last week. So now we start another topic, which is, so when I thought about the topics for this lecture, I hoped that I could talk about the topic that I will talk about today. And so this is a paper that was actually announced to be published, or not published, just put on the archive for last fall. But then it came out like 2 weeks ago. So I was waiting for this paper to appear so that I can talk about it here. And yeah, it was last minute that it appeared, so I can talk about it now. We start just with some calculations in finite fields. So we have two elliptic curves. Both over F5. Well, we have to take it as a black box, but you can believe that those two curves are isogynous, and that means that they have the same size over F5. But being isogynous does not mean they're isomorphic. And for two groups having the same size also does not mean the groups are isomorphic. So let's just find out what the structure of those groups is and see what consequences this has. So we had a few weeks ago, we learned how to compute those groups. We just, for p equal to 5, we just go through the elements of Fp. So we start with E. So this is 0, this is 2, this is 0, this is 0, and this should be 3. Minus 1 minus 2 is 3. And the root, well, mod 5, only 1 and 4 are squares, 2 and 3 are not squares. And here we have 0. Okay, so the points in E, F5 are the point at infinity, then 0, 0, 2, 0, and 3, 0. So these are all points of order 2 because they have 0 as a y-coordinate. So this is isomorphic to Z mod 2Z cross Z mod 2Z. What about E prime? X cubed plus x plus 2. Well, it's just plus 2 everywhere. So 4, 2, 2, 0. As I said, 2 and 3 are not squares. Root of 0 is 0. The root of 4 is 2 and 3. So the F5 points of E prime is the point at infinity, then 1, 2, 1, 3, and 4, 0. Now, since we know the points of order 2 are exactly those with y-coordinate 0, we know that this has order 2. And those 2 points don't have order 2 because they don't have y-coordinate 0. So they have to have order 4 because the group size is 1, 2, 3, 4. The divisors of 4 are 1, 2, and 4. This is the only point of order 1. This is the only point of order 2. They have order 4. And this means that the group is isomorphic to Z mod 4Z. Okay, so the first thing we see is that we have 2 isogenous curves. And over F5, the group sizes are equal, but the group structures aren't. This is Z mod 2Z cross Z mod 2Z. All the points have order 2. And here we have 2 points of order 4. Okay, one more example. Now we have 2 curves over F17. Yeah, actually I computed here by hand all the points, but this is actually not the point here. But we could compute all the points over F17 by hand. Or we could use a computer. Well, we can list the points and see there are 20 points. points. And we would also see that there are 3 points of order 2 because they have y coordinate 0. Which already means that the group is isomorphic to Z mod 2Z cross Z mod 10Z, because the only possibilities here, how the torsion points would divide, would be Z mod 2Z cross Z mod 10Z or Z mod 20Z, which would be the case if we only had 2 torsion points, points of order 2. So we do some calculations and see that this is the case. And we could do the same thing with the other curve. So some calculations. And would see that this is the same. Which is nice. So one question would be, first point is, when does it happen that the groups here are isomorphic, and when are they not isomorphic? And another question would be, okay, if they are isomorphic here in F17, what about finite extensions of F17? And well, if the groups are isomorphic, and can it happen that all finite extensions, over all finite extensions, the groups are isomorphic? And if not, basically, when does it stop being isomorphic? And this we will answer today. So we can continue with some calculations with these curves and F17. So what about E of F17 squared and E prime of F17 squared? Okay, so this is not so easy to do by hand. Well, theoretically possible because it's basically polynomials in one variable of degree 1 over F17, but yeah, there are 17 times 17, many of them, and this is crazy. So we don't calculate this by hand. We use a computer. And get that this is actually Z mod 8Z cross Z mod 40C, and this is this. So a few things that we remark here and that we want to find out if it's in the structure of the theory or if it's just a coincidence. The first thing is that already at the quadratic extension of F17, it stops being isomorphic. So the question would be, is that always the case, or can it stop at a later point? Second thing is, the group sizes are still the same, and the way they differ is just that Here we have a factor 2 more, and here we have a factor 2 less. So the question would be, is it always the case that if it breaks that way? So we have a first theorem that answers one of the questions. From 2018. Pretty recent for math research. So we have L, a prime number that's not 2. We have K, this field, and P is not 2. P is not L. But 2, I think 2 is allowed. And 2 elliptic curves. Ordinary elliptic curves. What that means is, well, for this lecture, not important, but it's basically, so when we talked about complex multiplication, we only talked about complex multiplication of elliptic curves over number fields or over C or over Q bar, but never about complex multiplication of elliptic curves over a finite field. And this is basically what it means. It should not have complex multiplication over the finite field, but you can just translate this as nice or generic. Okay, suppose each curve has a point of order L defined over K, and E and E prime are L isogenous. L isogenous just means that the kernel of the isogeny is of size L. Are L isogenous with kernel generated by a point defined over K. So those are the conditions. We are in a finite field. We have an L isogeny where L and P are different prime numbers. E and E prime are not extraordinary, basically. And then the K rational points, so K was the finite field Fp, of those curves are isomorphic if and only if they're isomorphic for all finite extensions. Okay, so in this setting that we have here, it means that if we are isomorphic on the ground floor, we're isomorphic everywhere. So here it cannot happen that in F17 we have the isomorphism, and in F17 squared we don't have it. And so why doesn't it apply to this thing? Doesn't apply to this thing because here we have a two isogeny. So the interesting thing is that here in this theorem, L is not equal to 2. We have some isogeny, but it's not a 2 isogeny, because 2 isogenies are different and interesting. So basically in this case, everything's fine and really nothing interesting happens because, well, if we have the isomorphism here, we have it in all finite extensions and everything's nice. So, but what else can happen? And what's so special about L equal to 2? And what happens if we allow L equal to 2? What different cases can happen? And the answer comes in the next theorem. Well, I would not prove it because it's a whole paper, and we could probably spend like a whole semester just on that paper. The same for the next thing. It's the same person 2 years later. Again, we have two ordinary elliptic curves, but now two isogenous. Defined over a finite field. Well, over Fp, and P is not 2. And the question is now, if we have an isomorphism on the first level or on the 0th level on the over Fp, so that's what I wrote here, what can happen? First possibility is that we have the same as here, that all finite extensions generate the same group. But the second thing is the interesting thing, because, yeah? Yeah. Yeah. And now the interesting thing is that if we have a tower of field extensions of Fp, then it breaks down already at the beginning. Yeah, okay, I still call it K. Oops, like this. So what it means that if we want to find out if the group structure is the same for any field in a tower of field extensions, we only have to do the first step. So we don't have to do complicated calculations in large towers of fields, and we don't know where we finished. No, we know it's already the unique quadratic extension that we have to look at. That for, well, small primes you could actually do it by hand, but for large primes also the computer is very fast in calculating this, which means it's actually possible to do calculations there. If we didn't have this and would have to calculate in infinite towers, then yeah, it would not be possible to do reasonable calculations. Okay, so this is a already a nice thing. We give this a name. So in the second case, where we don't have an isomorphism for any extension we call P, or also the pair of E and E prime anomalous. So sometimes we have E and E prime fixed and we look for primes that are anomalous, and sometimes we have a P fixed and look for pairs of elliptic curves that are anomalous, but both have the same name for this property, namely anomalous. But usually we fix elliptic curves and then look for anomalous primes. And if we fix a pair E and E prime, pair of elliptic curves, then we can also, of course, ask what condition for a prime P is there that it's anomalous, or can we maybe find, describe the proportion of primes, how they are anomalous. This is actually the theorem that made me interested in all this, where they actually found the exact proportion in one case of anomalous primes. And this is, yeah, it's February. This is from this year. This is really cool. In a lecture showing something that's very fresh research. Okay, so we have two elliptic curves. I will say something about those words. So E and E prime, rationally two isogenous elliptic curves over Q. This means we have an isogeny, kernel of size 2, and the isogeny is defined with rational coefficients, such that, and this would also not be possible without the last lectures, such that the image of their two-adic Galois representation so this was where we looked at the Galois group of two torsion points, then found a representation in terms of matrices after we chose a basis of the two torsion points, and then this image. This can be well, it lands in SL2Z or GL2Z, no, SL2Z, and it can have different sizes. I think the largest possible is something like order 6, but yeah, don't, I'm not very sure about this. But we calculated some images, and I think they were usually of size 2 or something like that, but we can, this can also be larger. And the condition here is that the image of this two-adic Galois representation is as large as possible. And for the moment, it's not important what that means, as large as possible, but it's important that it has something to do with this Galois representation and with the image of it. And then, remember, we fixed two elliptic curves, and at the moment they're only defined over the rational numbers. But of course now we can look at, we can just reduce it mod p. Well, if they are still elliptic curves then, but this will happen for almost all p, then the proportion of anomalous primes among all primes is 1/30. And yeah, the interesting thing here is, so what's the difference between this and this? The difference is that here we have L equal to 2, and there we didn't allow L equal to 2. And this is basically what comes after this thing. So here we found out what can happen. Well, it can happen that they're always the same, or that they are already different in the first step. And this says, okay, in the case, so the case where we find the difference in the first step happens in about 1/30 of the cases. And the theory behind is interesting. We will talk about the theory, but I think now is a good time for a break, then I can clean the boards. Okay, we'll meet again at 11:05.